Okay, here we have another composite system. This is a system of one converging lens and then one concave mirror, and they're placed as shown here in the diagram. Um, we start with, over here on the right, the general equation we use for these thin lenses and spherical mirrors. And then, as usual, usually we're interested in solving for the image distance. So in this notation, P is object distance, Q is image distance. So I take the general equation and I solve that for image distance. And then I have an equation that's just kind of ready to use, and I don't have to do this particular algebra for every single stage of the solution. So I'll start here. So we begin as usual, starting at the object and then kind of tracing the path of the light. In this particular problem, we're being asked to describe the final image made by the system, and we're told specifically here that we are interested in the image that's formed by light going through the lens twice. That's important information because otherwise we could kind of just keep going forever in this problem. So it's important to let us know how many times we're following the image around. We're told to describe it in as much detail as we're able to. So what we know about that is we can describe where the final image is, whether it's real or virtual, inverted or upright, and then the magnification of the final image. Okay, so we start from the object and we go through the lens. Oops, we go through the lens, and I'm just going to go ahead and say here um, that we're doing the lens, this is the first time through the lens because we're going to go through the lens twice, right? So I want to be really clear. And I like to label my work here. So when I'm looking at these, remember that our distances, our P's and Q's, are always with respect to whatever component we're working on. So if you don't label your work and you look back on your own work, it can really be hard to make sense of whether or not you are accurate on all your distances. So if you label everything, then it helps you to keep track of what you're measuring with respect to. So this is lens for the first time. My light direction is going to be going from the object toward that lens, right? So this is going to be the incoming light for that lens will be going left to right, and the outgoing light will be going left to right. So I'm talking about light that's going left to right. This is important because it has bearing on our sign convention. For a lens, positive object distance is positive when the object is on the side of the incoming light. Image distance is positive when the image is on the side of the outgoing light. Okay, so my first object distance, I'll call that P1, is equal to positive 5x. So there's my object, it's on the side of the incoming light, and I'm given that distance as 5x. So let me solve for Q1. Where's my first image? Let's find it. So that's going to be 5x multiplied by the focal length of this lens, which is given just as x. And that's over 5x minus x. This gives me 5x over 4 as my first image. Now let's figure out where that is. So if I go to my diagram, so 5x over 4, that's a little more than 1, right? So I don't know, I just kind of try to like 1, 2, 3, put where I think pretty much it's going to be. So that's the first image. It's good to physically keep track of this. Otherwise, it just seems like a whole lot of numbers and it's really hard to find your errors or to be aware of what you're doing. So when you're solving a physics problem, you should be aware of what's happening physically, or else you're kind of doing a math problem, right? So this first image is real. I can see that because my image distance is positive here. I can go ahead and calculate this first magnification as well and kind of be keeping track of the images. So that's always the magnification equation is negative q over p, right? So that's going to be negative 5x over 4, then divide that by p, so 1 over 5x. That gives me negative 1/4. So this first image, just this very first image, is real, it's inverted, and diminished. Okay. And then when you get something like that, one of the other reasons to stop and look at that is you can ask yourself, does that make sense for that lens, right? Like if that was an outcome that you got for a diverging lens, for instance, you would know that you made an error somewhere because a diverging lens cannot create a real image. It wouldn't create that type of image, right? So that's a reason to understand your components and then to look at what you get as a result. So that's the lens the first time. Let's go ahead and switch gears now and let's work on the light's going to now hit the mirror, right? And now our object for the mirror is the image that was created by the lens. So now we need to figure out what that object distance is going to be. That's P2. So that object distance is basically the distance from image 1, right, to the mirror. That distance right there, that's P2. So we need to figure out what that is. So that's going to be basically 3x minus 5x over 4. So that gives me 7/4 x. And it is positive because it's on the side of the incoming light. So for a mirror, the incoming and outgoing light are on the same side, right? We still apply the rule, the sine rule, but the incoming and outgoing light are on the same side. So that's a positive object distance. Now let's solve for my image distance for the mirror. I'll call that Q2. So that will be my 7/4 x times x over 4 all over 7/4 x minus x over 4. Kind of in a convenient form there. 7x over 24 is my image distance there. This is positive. I see again that this is a real image, right? So useful to know that. Again, I can ask myself, can this type of mirror make a real image? Yeah, a concave mirror can. So good. Now let's go ahead and calculate. We can calculate this magnification for this particular image. Oh, I want to actually note where this one is. So this image is 7/24. So, third-ish. I guess we can think about it that way. And that will be in front of the mirror. It's on the side. It's positive. The image distance is positive, so it's on the side of the outgoing light. It's really close to the mirror, right? So if this is 3, this is 1. So this is 1. I don't know. I'm just going to estimate in here. It'd be about right there. I'll label that as I2. So that's where my second image is. Magnification, again, is always, it'll be negative Q2 over P2. This was Q1 over P1 over here. So that's going to be negative 7x over 24. So over P2, right? So we flip that 4 over 7x. Be careful as you're working with these fractions. Negative 1/6. Always show your steps, and you know that the x's should cancel out, right, when you're getting the magnification, because your magnification is just a ratio. So this is negative and it's less than 1, so it shows me an inverted diminished image here. And remember that this diminishment, this 1/6, is with respect to image 1. It's not with respect to the original object. All right, so then that's our object for going through the lens again. So remember that we go through the lens twice. We're told that in this problem. So let's do that. So this is the lens the second time. And now one thing that's changed is my light direction has switched. So we'll go back and look at the diagram real quick. But now my light is going right to left. So that's important for considering my sign convention. So I'm going to actually erase these little arrows here because those don't apply anymore. And my light direction now is incoming light is going right and outgoing light. They're both right to left. Okay, so the incoming and outgoing sides of the lens are now different. Notice that image 2 is on the side of the incoming light. That tells me that it's going to be positive, so that's good. Now I need to figure out how far it is. Let me switch up a color here. So I'm interested in the distance between image 2, which is here, right, and my lens. So this distance right there is P3, and it's positive. Okay, so P3 if we figure out what that distance is, it's going to be 3x minus 7x over 24, and that will be equal to 65x over 24. When you're solving these, I should have mentioned this before, but don't use decimal approximations here. You lose information. And for optical systems like this, if you just like lose information every step, then your system's not going to be in focus. The pieces aren't going to be where they need to be. So it's really, really important not to use decimal approximations. You all have fraction skills, right? So just use those skills and express this stuff the way it needs to be expressed, please. Okay, so where's this image? Well, what do I have here? 65 over 24x times my focal length, which is just x. 65 over 24x minus x. And that gives me, there's some algebra steps in there, but I get 65x over 41 as my answer there. Again, that's positive. So that's a real image. This is my last image, right? This is the final image I'm creating. So I am serious about wanting to describe this because that's what the problem's asking for. So the final image is real. I know that because Q3 is greater than 0. Magnification for going through the lens this third time, negative Q3 over P3. So that's negative 65x over 41. And then invert P3, so that'll be 24 over 65x. And that leaves me with negative 24 over 41. So that's inverted and diminished. But remember, that's not the total magnification. We still need to calculate that. So when it comes to the final image, we know that the final image is real. So let's describe here the final image. So I know that it's real, right? P3 is greater than 0. I'm sorry, Q3 is greater than 0, the image distance. I know that it's located 65x over 41. Now that's positive, right? Positive image distance. That means it is located to the left of the lens. That's what that means. So 65 over 41, it's 1.5-ish, right? So this is 2.5. I don't know. I'm just going to estimate in here. Here's image 3. That's our final image. So it's located 65x over 41 to the left of the lens. So notice that just the image distance is not the same as the location because you need to use that distance in order to define the location in space. So it's located 65x over 41 to the left of the lens. That's an unambiguous way to locate it. The final image is real. We need to calculate the total magnification, and that's the product of all three, right? M1 times M2 times M3. So if you multiply those out, what is that? Negative 1/4 times negative 1/6 times negative 24 over 41. So it gets inverted 3 times, right? So that it's an odd number. That means that the final image will be inverted. And when I multiply those through, I get negative 1 over 41 here. So it's diminished, right, by 1 over 41, real small there. And that makes sense if you look at it. At every stage here, it's diminished, right? It's never magnified. Not all components will diminish and invert in this particular setup. And it's inverted. I know it's inverted because M total is negative. Okay, so I think that locates and describes our final image for this system.